yesterday's lecture, I kind of wrote down this eigenstate thermalization assumption. So it's basic. So I presented this as a result of wishful thinking because this gives you as one of the implications thermalization. Well, it did not come about quite as such because Srednich actually could derive it for certain classes of systems. So we'll come to this in a moment. So we will look at the evidence for this eigenstate thermalization hypothesis. So it's not so much a hypothesis anymore because we already have really good evidence about it. And we will also have kind of a look at the larger scale implications for equilibrium statistical mechanics. I mean, one of the implications that we already talked about is the fact that this generically allows you to understand thermalization. Yeah, the first thing I want to do, the first thing I want to do is I want to write down this kind of this ETH statement in a bit more specific details. So first of all, it is valid for a few body observables. And I'll give a very simple counterexample that it's not going to be true for all observables. So in a non-integrable quantum system, a non-integrable quantum many-body system, so my kind of definition for this for the time being would be some Hamiltonian that consists of few particle interact, as a kinetic term typically, and few particle interactions, and that has Wigner-Dyson statistics. So certainly not something that is quantum integrable in any sense, as we discussed 2 lectures ago. So now, the statement is true for the expectation value between nearby many-body eigenstates. And I would love to make the statement nearby more accurate, but to the best of my knowledge, this has not been looked at in detail in the literature, in the numerics so far. It is clear that ETH is not going to be valid if you just evaluate it between arbitrary many-body eigenstates, but they must be nearby in some sense. But what really sets the scale is not entirely clear. And you need to be away from the ground state. If you have a system with finite well, if you have a system with a maximum energy density, then you would also argue that you need to be away from the highest energy eigenstate as well. Okay, so under these conditions, the ETH statement is that the expectation value of this few body observable between these 2 many-body eigenstates, it first of all consists of, divided like this, it consists of a part that is diagonal and is multiplied by a function which is, this is a smooth function. And one can make this more accurate. It actually, so E bar is the average energy. So E bar is defined to be EM plus En divided by 2. So this function is smooth in the sense that the fluctuations are actually, again, exponentially suppressed in system size. So it's very smooth. And then for the off-diagonal part, this is minus S E bar. So where S is just the equilibrium entropy, the entropy of the system at this average energy. So last time we just wrote dimension Hilbert space to the -1/2. So in the leading behavior is exactly what's written down here, times a function that is again smooth in its two arguments. So omega is just Em minus En, and times a random variable. So and we have zero mean and unit variance. So this is kind of this ETH assumption written down in a bit more detail. Yep. Entropy. Yeah, entropy. I mean, so essentially you can write dimension of the Hilbert space to the -1/2 up to, you know, some factor that can also be extensive, but it's not going to be exponential. Okay, so the let's talk a bit about the evidence for this formula. So not necessarily for the formula in the way it's written down here, but for the structure of this. So the very first person who thought about this is actually Deutsch, and this is Physical Review A43 in 1991. And now the model that he looked at is he investigated a Hamiltonian that is basically, well, some diagonal part. Let's call it integrable because it's he writes it down in diagonal form, and then he adds a random matrix with some small epsilon to it, and then what he can show that because what this random matrix does is now it starts mixing the levels of H0 if you scale everything correctly, and this mixing of the levels means that even if you initially had eigenvalues of your observable that were different for the different many-body different eigenstates of H0, they become so strongly mixed because of this random matrix that the expectation value of your observable in the eigenstates of the full Hamiltonian is like an average over all of these, and that gives you this exponential suppression of the fluctuation. So that's the basic idea. For details, I refer to the paper. So even for small, so what he shows is that even for small epsilon, the fluctuations in the diagonal, the fluctuations for, let's say, I are exponentially suppressed. So of course this is so this with this random matrices one can show quite a lot, but of course this is not a microscopic many-body Hamiltonian. I mean, you write down something which has the captures certain properties of a non-integrable Hamiltonian. I mean, obviously this thing, for example, has Wigner-Dyson level statistics the way it's constructed. but this is not a genuine, like many body Hamiltonian with some kind of interactions. Somehow more, maybe better known is a paper by Mark Srednich from UCSB. So this is also, this is PRE 50 in 1994. And he's also the one who actually coined this term eigenstate thermalization hypothesis. There is another paper which is 1 year later, which is actually kind of I think gives already a clearer picture of the whole situation. But this is the first paper, and what he is looking at is a quantum system in a semi-classical limit. So a quantum system where you can do some semi-classical approximation, and the underlying classical system is chaotic. So you're looking at the semi-classical limit of a quantum system that in the classical limit becomes chaotic. And now we do know a lot about classically chaotic systems, and so what he can, so this is one assumption, and the other assumption is that the observables are smooth functions of the position and the momenta of this particle, of the particles, and then under these conditions, he can essentially show this part and argue that this part should also have this structure in the old formulation that I gave you with the dimension of the Hilbert space to the power -1 half. As a side remark, Deutsch only makes a statement about the diagonal. He doesn't say anything about the off-diagonal. And so this is actually a very nice result, but it applies to a very specific class of quantum systems or quantum many-body systems, namely such that we can treat in a semi-classical limit. And of course, many of the systems that we are interested in cannot be treated in that way. I mean, take a regular spin 1/2 chain or interacting fermions. So this is the fact that one can show this is not enough yet to really believe ETH. Yeah. Small h bar. Small h bar. Yes. So you do basically you do an expansion in h bar. System where you can do an expansion in h bar. Or equivalently, for example, there are models where the role of h bar is played by 1 over some large parameter, 1 over n. Yeah. So in a large n limit. Yeah. That would be in a large spin limit. For example, there are one nice system that you can think of is, for example, you take lots of let's say spin 1/2s, and they are all coupled with one another. Yeah, so you have a fully connected lattice. All the interactions, all the couplings are equal. Then you can map this to a large spin, one large spin, n over half if you have n spins. And then if you write down the basically if you write down the dynamics in this large n limit, then you see that in order in leading order, you just get some classical dynamics in some potential. So that would be basically the classical limit. And then the leading 1 over n correction that would be the leading quantum correction. Yeah? That's also easy to describe, this leading quantum correction. That essentially just means that you do some Liouville dynamics where you basically your initial quantum state that you're interested in corresponds to some probability distribution in Liouville space, but you evolve this again classically. So again, the leading correction is easy to do in this way. And for example, approximations like the truncated Wigner approximation and so on, something that Anatoly Polkovnikov has worked on a lot. That's also in the class of the semi-classical approximations. So the trick is basically you have something which is classically chaotic, and your first quantum correction it's a small correction in a parameter that you can control. And the dynamics of this first quantum correction is something that you can actually kind of relate back to the classical dynamics. So the technical ingredient here is Berry's conjecture and Schnirelmann's theorem for the ones who want to have a really close look at this. I want before continuing and looking at numerical evidence for systems that cannot basically be that are not in this class and not in this class over there, I want to make one kind of remark already. So note, ETH is not true for all observables. So again, we are in the situation that we need to carefully consider what kind of observables we are looking at. For example, it is not true. That's the popular example that people write down. You just write down a projection operator onto one of the many-body eigenstates of your Hamiltonian. This thing is absolutely not smooth. Yeah, it is one if you evaluate it in this many-body eigenstates, and it's always 0 between any other many-body eigenstate. So this is clearly does not fulfill the ETH assumption. But this, for a quantum many-body system, this projection operator, if you wanted to write it down as in, let's say, creation and annihilation operators of your fundamental field, it would be an incredibly complicated object that would probably contain as many creation and annihilation operators as your system has degrees of freedom. Yeah, so that's not something that you can really measure. But again, it shows that we need to think carefully about the class of observables for which this assumption is valid. Yeah? Sorry, on? Oh, I do. I do, but it's so this is one of the kind of the outlook questions that I wanted to present in the end. It's most likely going to be the end of the lecture. So the way, I mean, maybe as a preview, but this is what I'm saying is words. So this is not, it's not math. Yeah. So the way I think about it is, if you think instead of thinking about many-body eigenstates, think of Anderson localization. So few body, basically one-body eigenstates. And now, if you think about the structure of these eigenstates, if you have eigenstates that are essentially that are nearby in energy in the delocalized part of the spectrum, yeah, they have a very different structure everywhere because of mixing, small energy denominator mixing. Yeah, so if you evaluated any kind of local observable between these two many-body eigenstates, it would just give you 0. Exactly, and somehow this is how I view this in Fock space. Yeah, so in a way, I mean, I said this is just words. In Fock space, these two many-body eigenstates have a very, very different structure. Few body observables act somehow locally in Fock space, And because they have a very different structure, their overlap is 0, unless you take exactly the same many-body eigenstate. And the structure is so different because they are nearby in energy, therefore they get strongly mixed. And I mean, just basically what happens if you start mixing nearby eigenstates. Yeah, exactly. Yeah, yeah. They have a very different structure. If you think like in Anderson localization, the eigenstates have a very different structure in position space. And here somehow they have a very different structure in Fock space, such that a few body observable that in some sense acts locally in Fock space can't connect them. Yeah, if you could make this accurate, I would be very happy about that. Yeah, but this is how I view this. And you also kind of see that this kind of assumes that you have level repulsion, that you have Wigner-Dyson statistics. And it doesn't help you at all if you look at eigenstates that are very far away in energy, because you can't make this argument. Yeah? Mm-hmm. Yeah, exactly. Yeah, but that's what I was saying. I'm just using words right now. I'm not doing math. I mean, you would really need to try to, this is kind of an intuitive picture that I'm presenting. This is how I think about it. But it is quite hard to make this more accurate. I mean, I think this is my one key outlook question: a better understanding of ETH. Because I mean, so far we have two specific situations that certainly don't cover everything that we are interested in. We have numerical evidence that I'm presenting right now, but we have no underlying analytical picture of ETH. I mean, at least, there's nothing really, published in the literature where someone comes up with a unified picture of what this means. Then ETH is so important that this would be really very worthwhile having such a picture. But it's a hard problem. The next is I want to show you some numerical evidence for ETH. I mean, there is a lot out there by now. So the main person to mention in the context of this eigenstate thermalization, still called hypothesis, should never name a theorem, or you should never name something hypothesis, then it's always going to be a hypothesis, however much evidence you have for it at some point. So as Marcos Rigol, so he was one of the persons who really started with collaborators, but I think he was the main driving force for establishing ETH in a variety of quantum many-body systems. So here, this is a Nature in 2008, which I highly recommend. He studied hardcore bosons on a 2D lattice. I don't want to write down the specific lattice geometry structure right now. And here, this is now on this 2D lattice. This corresponds to a non-integrable system. And here he takes two different eigenstates. So this blue, this green and the blue, you can hardly see the difference here. And what he plots is some momentum distribution function. So this is no non-equilibrium dynamics right now. We just look at the many-body eigenstates and evaluate observables. So the only thing you need to do is you need to diagonalize your Hamiltonian and evaluate the expectation values. And you see that this momentum occupation function as a function of the one of the momenta. I mean, for these two eigenstates agrees perfectly. Yeah, you can't see any difference. Over here, it's the 1D version of the system with periodic boundary conditions, and this is actually an integrable system in the hardcore limit. So we only look at the green and the blue lines, and you see that these two certainly do not agree. Yeah? So there's large fluctuations between these two. So these observables are certainly not, the expectation value of these observables in these eigenstates are certainly not identical. Now down here, this is the zero momentum component of the mode occupation number, plotted as a function of the basically the energy of the many-body eigenstates. So here you go through the whole spectrum, and so what you would like to see is you would like to see that this is a smooth function, yeah, with little scatter. And you can see that this is, reasonably well fulfilled. Yeah? You can also see that it gets worse at low energies here where you approach the ground state. And again, this is not surprising, yeah? Because ETH is only going to hold somewhere in the spectrum away from the ground state. And again, this is a notion that I would love to make more accurate. Over here is the same for this integrable system, and you see there's large scatter between the, if you just go from one many-body eigenstate to the next many-body eigenstate. So this was one of them, was the first paper, and here this is now something later. Again, hardcore bosons in one dimension with periodic boundary conditions, and now you introduce this next to nearest neighbor term, which makes the model non-integrable. And so this here are now plotted simulations for different system sizes. So you want to see that these fluctuations are suppressed if you make the system larger. And again, what is plotted? So this is the serum momentum mode occupation, and this is the kinetic energy per site. And for this integrable model, basically as a function of, basically here where you just go through all the different many-body eigenstates, you have large scatter in the expectation value, not so much for the kinetic energy per site, but as you turn on this integrability breaking term, you see that this thing starts to shrink quite a bit, both here, and you can also see that. So the green dots are the small system and the red dots are the larger system. You can also see that this curve starts to shrink. There are other studies that show that the way it shrinks is also consistent with the scaling behavior over here. Yeah, of course, it's very difficult to get these numerical results, because you have to deal with an exponentially large Hilbert space, and you can't go to really very large systems. So this is some of the evidence that that is around. Okay, so I leave this up for now, and I want to say a bit more about the implications of ETH. Yeah. Oh yeah, you could easily. I'm not sure. I need to look up what the specific conditions here are. I mean, generically, I mean, at least if I think of fermionic systems, if the system is integrable, it's usually integrable for any kind of filling. So right now, I don't know of an example for a situation that you are describing, but I also can't rule it out. Are you aware of an example? I can't answer this question right now. I mean, if you want to think about the connection between something which is localized in a conventional sense and ETH, I mean, that would be basically, that would fall under the umbrella of many-body localization. Because, I mean, that would be, I mean, you can think of a many-body localized spin system. I mean, this basically, the starting point is a very strongly disordered spin system. So, and in a way, the conservation laws that you have as you go away from this very strong disorder limit, these conservation laws tell you something about if you have a spin excitation in some region, that even if you wait very long, that there will be a memory of that spin excitation because you have an overlap with a localized state. So I think if you want to think about this direction, I would look at it under the umbrella of many-body localization. Yeah. And for many-body localization, basically, it is that if you start with the strongly disordered, you could call it localized phase, then you end up in a phase where ETH is not valid. And if you are in the delocalized phase, you end up in the phase where ETH is valid. And this transition between many-body localized and delocalized is similar to the Anderson localization transition. It's a transition only on the level of the eigenstates. Okay, so I want to say something about an important implication of ETH beyond giving us a very compelling picture of how thermalization happens. That is implication for quantum statistical mechanics in general. And so, so one way of kind of saying this, what this mathematical statement means, is that for a non-integrable Hamiltonian, an eigenstate, any eigenstate away from the ground state, so I'm not going to write down all the trivia. Any eigenstate is typical within some small energy window. Yeah, as I said, I'm not aware that we have a very precise meaning of what this is, but certainly within any kind of nearby many-body eigenstates. And so what this means is that all the eigenstates in some window E minus delta E, E plus delta E, that they are actually indistinguishable for all physically relevant observables. Yeah? Because you cannot distinguish them. You cannot come up with an observable that would give you an expectation value that distinguishes them. So they are indistinguishable for let's say for few body observables. Few body observables. So, and from one point of view, knowing all the eigenstates is actually complete overkill because it doesn't give you new information, at least within some small energy window. So there is some kind of, I think we talked about, some universality in this, similar to level statistics, yeah? You don't really learn anything new if you look at this level. If you know one of them, you know everything already. This is really a very, very strong statement. And that's, I think, why it would be so important to kind of nail this down more accurately. And so one of the consequences, I think it was specifically David Hughes who kind of pointed out the importance of this. So if you look at something which we do in textbooks at the microcanonical ensemble, so the way we write down the microcanonical ensemble is that we construct a density matrix that consists of all the eigenstates in some small energy window, and then we argue, okay, this coefficient Ci, we choose them such that the von Neumann entropy gets maximized. So, of course, this implies that this is just 1 over the number of states. So just 2, that they're all equal. And now you can, I mean, a microcanonical ensemble describes an isolated system, and you can very legitimately ask the question, I mean, why should this actually be true? And, you can talk more about this, but there is no, there's no really fundamental reason to believe that this should be the correct construction principle for them for this ensemble. And the nice thing with ETH is that it does completely away with this, because what ETH tells you is that implication all choices of the Ci, of course, they have to be non-negative, and they have to sum up to 1. All choices are identical in the sense that you cannot physically distinguish them. So you can even replace the microcanonical ensemble by just one of the many body eigenstates in this window. Yeah. I don't think people have thought about this. I don't think people have thought about it. I'm not aware of people looking at ETH for some non-integrable gauge theories. So yeah, no, I'm not aware of that. I'm not aware of that. Mm-hmm. So I can only give you an answer based on what I tried to do. So I tried to use ETH for OTOs, and I didn't get anything. So that doesn't mean that. It just means that I did not manage to make a connection. Yeah. And for the people who don't know what out-of-time order correlators are, you can come and ask me later. But this takes a bit of time. Yeah, I mean, there's numerics, or? Yeah, of course, numerically you will see similarities, because, I mean, you expect chaotic behavior, so out-of-time order correlators with some exponential behavior for non-integrable systems. For non-integrable systems, you also expect ETH to hold. So this is more points to the fact that the underlying reason is that you have a non-integrable many-body system, as that there's a direct connection between ETH and OTOs. I mean, I think the way to think about this is to only take the ETH assumption and see if you can derive OTO behavior from that. And that, I think, is, at least I think, not possible. So I think a numerical work just shows you that there's a correlation, but that doesn't mean that there's a causal connection. Okay, good. Okay, so this is this is, I think, really one of the really, really important things that one has learned in this field of thermalization. And I think at some point maybe this will also enter into textbooks, because it really gives you a different picture of quantum many-body systems. Yeah. Sure. Yeah. You need, of course, to take all the, all the global conservation laws into account. Yeah. I really don't know. It would be worthwhile in numerical. I mean, it's probably going to be a numerical study. I don't know how else you would want to do it. It would be a very worthwhile numerical study. And I'll check the literature first, but I think it would be a very worthwhile numerical thing to do. Of course, you need to see how far you can push the numerics. Yeah. It's going to be harder than for these systems. Yeah. But it would be very interesting to check. I mean, for example, the first thing would probably be to think about level statistics in these systems in the first place. I don't know how much is known about that. I mean, there you can already ask this question. What kind of conservation loss you need to take into account? Okay, good. So, okay, so okay, so after ETH, so let me just show you one more slide. So this is a figure from Rigol et al.'s original Nature paper. So this is a nice picture here. So over here, this basically shows you the dynamics again. If you assume ETH, so you have your initial state that is some superposition of many-body eigenstates. Each of these many-body eigenstates is thermal in the sense that they are all typical, but at short times you still have these all these phases that you get during time evolution are still haven't decohered yet. So you can have an expectation value of an observable in the superposition that is not just basically the sum of the expectation values of these in these individual many-body eigenstates that are all identical. Yeah. So here you have the coherences, and that's why an observable is not just the expectation value of an observable is not just given by the expectation value in one of these many-body eigenstates, because you have to take the coherences in the construction of the state into account. And if you wait long enough, then essentially you think of it as just an ensemble of many-body eigenstates, and you can evaluate your observable in either of them. They all give you the same answer. So this would be kind of the picture underlying this thermalization dynamics. And again, there's a few things that one would like to make more accurate. Yeah. Yeah. At short times, yeah, exactly. I mean, one of the reasons for that is, I think, is that that in your initial state, you also have contributions of many-body eigenstates that are somehow further away in energy. Yeah. Yeah. So yeah. 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 Yes. Yeah. Yes. Right. So that you don't need to take these overlaps into account between eigenstates that are actually more different, where you can't apply ETH. Then you also need some kind of decoherence argument. Yeah, but that would be my picture. That would be my picture. Well, for integrable systems, what you have here are eigenstates that can give you very different expectation values for your observable, because you have more conserved charges. So there's no reason to expect that the expectation values are identical, and they are not identical. I mean, one can look at the numerical examples. So that means that the kind of superposition you get here at large times, I mean, the kind of coefficients that you have in front of them will show up in the expectation value of your. So now I want to say a bit about the topic of prethermalization, and this is something that, this is something that I've worked on quite a bit myself, and this is actually something that, in the context of this quench dynamics, started with this paper with a former PhD student of mine, Michael Möckel. So I want to just tell you how we came about this prethermalization ideas, and then I'll put it into a bigger picture. So the question that we were interested in is the following. So we were interested in quench dynamics, and specifically since my background is condensed matter theory, we were interested in Fermi liquid theory. And now we know that the Landau picture is that you switch on the interaction adiabatically slowly, very slowly, and then you have this one-to-one correspondence between the physical electrons and the quasar particles. And so the question, and then the momentum distribution function evolves in this characteristic way, where at 0 temperature you still have a non-vanishing discontinuity at the Fermi edge. And the question that we asked is, okay, what happens if you switch suddenly? So basically, just the opposite of what Landau is telling us. So we switch on the interaction suddenly in the system. So what we found, so this is an analytical calculation, is that there is a time window or regime. I'll show you more about this in a moment, where you have something which can survive for a pretty long time, a state which is called prethermalized. So the term prethermalized that was introduced already earlier for a specific class of states with certain properties by Berges et al. And so what happens in this setup is that in this time window you have a momentum distribution function that still looks kind of discontinuous at the Fermi energy, except that the size of the discontinuity is different from the size of the discontinuity that you have if you switch it on very slowly. Now one can, sorry? Capital D, where is? Oh yeah, that's one about the bandwidth. Bandwidth, yeah, that's the bandwidth. Well, hopping matrix. Okay, so and one can also figure out that this discontinuities here, they are related by a simple factor of 2. So it's a nice simple calculation that shows this. Now this kind of picture was then very nicely confirmed using a numerical simulation. So this is basically in a specific limit of infinite dimensions for the Hubbard model by Eckstein, Koller, and Werner. And what is plotted here is from their paper is this discontinuity at the Fermi energy as a function of time for different interaction quenches. So you start from the Fermi gas at Q equals 0, and then you switch on the Hubbard interaction. And you can see, of course, you always start at 1. That's well, it's basically here. And then you have this initial phase where the discontinuity gets smaller on a time scale set by essentially the lattice, the hopping parameter of the lattice, the bandwidth. And then you settle into a regime where nothing seems to happen for some time. Yeah, this can be very long for weak interaction quenches, and it becomes shorter for larger interaction quenches. And these dashed lines, that's exactly the predictions that we had made here. So one can see that there is kind of this something emerging here in this the quench dynamics. And then if you wait for even longer times, then actually the momentum distribution function starts approaching a thermal Fermi-Dirac distribution for the electrons. So this is the picture, and yeah. Yes, there is. So for this, I would like to refer to the paper. There's a simple calculation that one can do that shows you why there needs to be exactly a factor of 2. So that's a very general statement that one can make about certain kinds of time averages, which applies to this situation. So I mean, I could draw things at the blackboard right now, but I think I would refer you to the paper where we do the calculation. Yeah, it's pretty straightforward, actually. Yeah. Yeah. No, it's basically the picture is generally applicable in at least 2 dimensions because you have to avoid 1 dimension, and where we did our the kind of the more numerical calculations, that was always in a d to infinity limit, because then it becomes. But the argument holds. Yeah. The argument holds. Yeah. I'll give you the general argument now. Yeah. Yeah. Yes. You could translate that. Yeah, you could translate that. Yeah, you could translate that. But I mean, the argument that we present where this factor of 2 comes from is based on really studying the momentum distribution function, because the momentum distribution. I mean, these NKs, they have a specific property. They commute with the initial Hamiltonian, and then. And under such conditions, if one switches on an interaction, one can show a general statement about the expectation value of this observable in the interacting ground state, basically with this perturbation switched on, with respect to the time average of the expectation value of this observable if you start a quench from the ground state of H0. And this, basically, in this calculation, you get this factor of 2. So for a discrete quantum system, it's a very straightforward calculation. It's just basically perturbation theory. Second order perturbation. Okay. So the main kind of conditions that that in my opinion are important for this scenario is that we have a many-body Hamiltonian with an underlying quasi-particle picture. This is true in most systems. With an underlying quasi-particle picture. And the other thing is that we are looking at a weak quench. Don't have to start from the non-interacting ground state, but it should be a weak quench. Also, you can see here this kind of pre-thermalization regime is pronounced if you have a weak quench, and it becomes it kind of disappears if you make your quench very large. And now, so the physical picture, what's going on here? So this is you start with the ground state of H0. So what happens is that, so let's draw a time axis here. What happens is that we have first a regime, and the typical time scale would be something like 1 over the bandwidth. And what happens here is quasi-particle buildup. So here in this context, the physical electrons get dressed by electron hole excitations to become quasi-particles. So this happens very quickly. Then we have this pre-thermalized state. And now this can vary, but you can say that the generic time scale is like 1 over the interaction quench squared. So this can be a pretty long time window. And now this pre-thermalized state has, and so then first of all, let's do this. And then out here we have thermalization. And this is just described by a conventional quantum Boltzman equation. So what happens is that quasi-particles form, but they need some time to find each other. Yeah. So the collisions only set in here. So the quasi-particles form quickly, but then the time scale that is relevant for the collision term in the Boltzmann equation corresponds to a time scale that can be pretty large, and therefore one has this window where the collisions between the quasi-particles don't yet play a role. So one way of describing this is that one can actually describe this pre-thermalized state by a generalized Gibbs ensemble, where the conserved quantities just correspond to the mode occupation of my quasi-particles. Yeah? And this is so these are of course not truly conserved, because we know that we have scattering processes describing quasi-particle scattering in the Boltzmann equation, but in some time window, these scattering processes might be unimportant. It might be a large time window. And therefore, on this intermediate time scale, the system can basically be described by a GGE. The term pre-thermalized was originally introduced in a different context. So what one finds here is that if you look at local quantities, so some local expectation value, they are already thermalized here. But the momentum distribution function is not yet thermalized. So yeah, because I mean, as I showed you on the slide before, I mean, it still has something which looks like a discontinuity and so on, so it's certainly not thermalized. But so the energy distribution over modes is non-thermal. So you have basically, you have the energy in your system distributed over the various modes in a non-thermal way. And the way it is distributed over these modes in a non-thermal way is just basically your GGE, because you have these conserved quantities, and basically the mode distribution is just determined again by essentially Lagrange multipliers that you can calculate in the ground state package now. And now this mode distribution is not going to be stable. This energy distribution over the modes is not going to be stable, because we have, this is not an integrable system, we have scattering processes, we have diffractive scattering between quasi-particles, so they will change the energy distribution over the modes, and this is what sets in here. Yeah? So one can think of this, there is basically, this is some kind of novel state that emerges on an intermediate time scale. Yeah. The final Fermi-Dirac distribution forgets everything. It only remembers the quench strength, because the quench strength gives you the excitation energy density. So the only memory over here is the excitation energy that you have when you look at the initial state in the Hamiltonian that drives the time evolution. So you can calculate this. This is what we've done as well. So you can calculate the excitation energy density. You can figure out what's the corresponding beta. And that's, of course, the beta that comes out in the thermal distribution if you wait long enough. So if you wait long enough, then the only memory about the initial state is this one thing. However, if you have this pre-thermalized regime, then you also have a memory of how initially the energy is distributed over the, basically over the modes of the system, and these are basically here the quasi-particles. Because they are in a way well-defined, conserved quantities if you forget about the Boltzmann equation. So, but this memory then gets lost because of the quantum, because of the kinetic equation dynamics. Yeah. So this time scale here, this would be, so if you have a let's say this would be 1 over the Fermi energy, or 1 over the hopping matrix element. Yeah, and here this would be if you quench from u equals 0 to some u, so this would be u to the minus 2, or rho times u to the minus 2. And then I need to introduce dimensions again. So for a weak quench, you can make this arbitrarily large. I mean, what do you mean by high? I mean, this is it's a non-equilibrium. Mm-hmm. I mean, I'm not really sure, because I mean, I actually wouldn't make a comparison there. I think it's more misleading than helpful. Yeah. So here, this is the. So this is basically, this gets thermal energy distribution. Due to kinetic equation dynamics. So here, this would be u to the minus 2. So if you quench from u equals 0 to some non-zero u, it would be u to the minus 2. Yeah, that's when basically that's the time scale where the scattering processes, basically that's the time scale of the scattering processes. I mean, this is how much time the quasi-particles need to actually see each other. Yeah. So one thing I kind of like about this picture is also that this is now for a so this would be for a non-integrable system, for a weak quench with this kind of picture, with this kind of conditions. This would be the kind of the generic picture of what we expect things to happen, and this has been found in a number of systems now. If we compare this with an integrable system, well, it's actually very similar. It's actually very similar. The only difference is that this pre-thermalized regime now extends to all times. Yeah, so the difference between something which is integrable and non-integrable is basically the fact that for the non-integrable situation, this pre-thermalized state becomes unstable because I have diffractive quasi-particle scattering, whereas for an integrable system, yes, the first time scale is dephasing. So this time scale here, this is essentially what's happening here is dephasing. Yeah, so it's kind of like you have the wrong kind of basis initially. The right kind of basis are quasi-particles because they hardly interact. I mean, they only start interacting on a large time scale. So you have the wrong kind of basis initially, and what happens is that you have some dephasing dynamics going on, so that essentially you can drop the off-diagonal matrix element in this correct basis. And this is what you can also call quasi-particle buildup. Yeah. So that's exactly dephasing dynamics. So this first part, so from here all the way to here, this is something that is fairly easy to do in perturbation theory. This is easy to capture, yeah? And this is how we did the calculation back. So this is something easy to capture. Yeah? Yeah, yes. Yes, there is a paper, I didn't write down the reference right now, by Fabian Essler, Neil Robinson, Salvatore Manmana, and myself, I think 2 or 3 years ago, where we studied exactly this. Yeah, so kind of controlled integrability breaking. This picture, yeah, and you can shrink this pre-thermalized window basically depending on how you're interacting. I was hoped to talk about irreversibility. This is something that I'm actually currently working on, and this is something that I worked on, I don't know, scary number of years ago. But I think instead of, the time doesn't really allow that. So I wanted to wrap up now with outlook and some, I think, interesting questions. And so maybe we can talk more about that. And there's one thing that I wanted to talk a bit more about, which I find very interesting and which is still missing from this picture. Yeah. So just the conventional quantum Boltzmann equation. So you write down a Boltzmann equation, and and basically in the collision term you build in the Fermi-Dirac statistics as usual. You build in the Fermi-Dirac statistics as usual. So you have a collision term that you have a collision term that no, what do you mean by approximation for the collision term? The collision term you evaluate typically in second order perturbation theory, but then the whole collision term on the right-hand side, of course, has to contain the correct quantum statistics. Let me write it down. Oh no. So first of all, this is why this is important. So the quantum Boltzmann equation is actually an equation for the quasi-particles. Yeah, it's not an equation for the physical electrons. It's sometimes confused. Yeah, so it's an equation that describes the quasi-particle momentum distribution. So the quantum Boltzmann equation, as its input, needs a quasi-particle distribution. So you can't apply it here. It makes no sense to apply it here. So the quantum Boltzmann equation description can set in as of here when you can think of having well-defined quasi-particles in your system. And if you do that, then you also see that nothing happens on this time scale and something happens on this time scale. Yeah, so this initial dephasing dynamics is very important to actually come to a point where you can use the quantum Boltzmann dynamics. Yeah, otherwise you get nonsense right away. Yeah, so is it clear how the exchange statistics part looks like, or shall I write it down? You can only write it down for the quasi-particles. So that's number. Sorry? Okay, we can discuss this more later, but let me just say the following. If you apply, for example, if you decided to look at the Fermi liquid in equilibrium at 0 temperature, and you took this momentum distribution function, this is the one for the physical electrons, and you plug this into a quantum Boltzmann equation, basically naively using the distribution function of the physical electrons, yeah, then this distribution function is, of course, not stable under the kinetic equation, and it would thermalize. Yeah? So this is not stable if you do a Boltzmann equation just where you put in this momentum distribution function. Yeah? So that's my short answer to this. But we can discuss this more later. So the quantum Boltzmann equation, so here you have your collision term, so I, K1, K2, K3, K4. So here we have scattering process, K3, K4, and then now we need to remember that in the gain term, the states in which we scatter have to be unoccupied, and the states that we scatter from have to be occupied, and minus the loss term. Spare me writing this down right now. Yeah? Okay. So if you have, of course, if you just have the usual kinetic equation, then you don't have to worry about these factors. Then you just have nk1 times nk2 in the gain term. Okay, so some questions that I believe are really important. Outlook and some key questions. So, number one, as already discussed, is ETH. And so an analytical understanding trying to turn maybe the intuition that I try to present into something that's actually a real argument. So that would be really worthwhile because, I mean, ETH has really changed can change your way of thinking about statistical mechanics for generic many-body Hamiltonians. And a lot of the work, most of the work has focused on numerics. So there is certainly room for doing something analytical. Then another question that is reversibility versus irreversibility. So if we think of thermalizing dynamics, we think of this as something which is irreversible. And this is what I actually originally wanted to talk about today. So this is a topic that has not been explored a whole lot so far as compared to the whole story of thermalization. It's related, for example, to these out-of-time order correlators. Since I'm not going to talk about this, I just want to mention one paper that we had on this question of reversibility versus irreversibility in quantum many-body systems. And of course, I'm happy to talk more about this after the lectures. So this is something we published last year. Another topic that I think is really interesting. Or let me maybe say a few sentences about this. So the question of irreversibility, of course, is a question that already arises in classical statistical mechanics, and I will just show you the introductory slide. The introductory slide of this of the talk on irreversibility. So basically, this question goes back to how one can reconcile the second law of thermodynamics with microscopic time reversal invariance. This goes back to the basic debate that Boltzman considered the H theorem an analytical proof of the second law. So H decreases, or we would call it S equals minus H increases as a function of time, and of course this is what comes out of the kinetic equation, the Boltzmann equation, and Loschmidt objected to this basically by pointing out that if something is time reversal invariant at a microscopic level, you cannot derive an equation from it which violates this condition. And the answer to this by attributed to Boltzman basically is very insightful. Well, you talk about changing all the velocities, then try to do it. Yeah. And it's a very deeply insightful answer because it really captures the main feature of irreversibility. So Thomson, who's better known as Lord Kelvin, so he explained this very clearly. If you have a generic system, a classical system with many particles, if you let it evolve for a long enough time, then any slight deviation from absolute position in the reversal will make it impossible to go back. Yeah? So on a practical level, we have a classically chaotic system. So we have exponential sensitivity. So a time reversal operation requires exponential increase in accuracy with the waiting time. And this is what you mean by classical irreversibility. Yeah? So of course, you can go back in time if you evolve your equations back in time. But you can't do it in practice if you have this. And this is what you mean by irreversibility. So the question that we are interested in, this is the situation for classical systems, and we are interested in how can one talk about reversibility versus irreversibility for quantum many-body systems. So if you evolve your system forward in time, and then you perturb it a bit, and then you run backward in time, in a chaotic system, the trajectories, they diverge exponentially. So you can ask the question, how small a perturbation is allowed? Yeah? And because you diverge exponentially, the accuracy has to decrease exponentially if you want to have the same kind of accuracy on the return trajectory. Yeah? So this is something that we've been interested in, sorry, Les? I actually don't necessarily think so, but so we have some results on it, but as usual, this is results for specific models and so on in the specific situations. I don't know how general a picture I can make out of it, and there's a lot of room for doing work here. Yeah, we think that the concept of irreversibility should be closely related to the concept of thermalization, but I think that there's a lot that one can still understand here. Yes. Yeah, so what we find in our numerical studies for non-integrable quantum many-body systems, or spin chains basically, what we find is, again, an exponential decay. That's what we find. We don't know how to calculate the rate, which would be the Lyapunov exponent. We have no idea how to calculate that. But what we find is, looks like exponential. The numerics is really, really hard. It's really, really hard. This kind of echo dynamics is terrible because you think in terms of entanglement entropy. You go forward in time, the entanglement entropy in your system goes up, it makes it really hard for numerics, and then you go backward in time and it goes down again. Yeah. So numerically this is not easy, and also all kind of approximations like kinetic equations, where the entropy only increases, of course, completely useless for this kind of investigation. So the zeroth order investigation in this question is kind of hard. You have to get a zeroth order answer. Yeah. Did he study some echo dynamics? Maybe you can show maybe you can show me the paper because I'm not aware of it. I'm not aware of it. Okay, so yeah, so there's a lot of space for working on this. And then, well, something we already heard about, periodically or quasi-periodically driven system. With respect to a steady state and whether there is some pre-thermal regime, there's also lots of interesting questions out there. Then one point is method development, especially in more than one dimension if we are interested in non-equilibrium quantum many-body systems. Because if you look at what most of the stuff that I presented, apart from the last part, is on one-dimensional systems. And that is because integrable systems are typically one-dimensional, and because you can do good numerics in one dimension. So it's driven by, it's kind of, so a lot of the research is driven by what you can do and maybe not what you should do. Yeah. So to have methods available also in higher dimensions, I think would be very helpful. I'm not sure if I expect completely new things to happen, but unless we have the methods to actually look at it, we won't really know. Mm-hmm. Yeah. Yes. Terrible. Yeah. Yeah. I mean, so what happens if you look at a method like TD-MRG, for example? So this is now my favorite spiel on TD-MRG. Yeah, time-dependent is a time-dependent DMRG. But basically, what happens if you look at this non-equilibrium problems, you run into a wall that your entanglement gets too large, yeah, and then you can't do your numerics anymore. And this is kind of strange because what we have learned is that, at least for some generic systems, we expect the system to thermalize. So in a way, TD-MRG doesn't work anymore. But we actually know that things are easy. Yeah, I mean, you might even be able to do something analytical if the temperature is high. Yeah, so it kind of also tells you that the DMRG methods, because they keep track of the kind of the full wave function, it kind of keeps track of too much information, and this sounds a bit like ETH. Yeah, and so you run into a wall that maybe shouldn't really be there. Yeah. But the quantum kinetic equation. No, people haven't really explored this very much. I think it would be very worthwhile doing that. So also going away from a one-time, let's say, to a two-time approximation. I think that because I think actually with doing the two-time approximation, you should be able to capture the whole picture from quasi-particle build-up to thermalization in one consistent framework. I think that would be, and that would also be something which, of course, you can specifically use in higher dimensions. So I think it would be very worthwhile. To the best of my knowledge, it hasn't been done so far. But I think that would, and this kind of a tool would also be really helpful for echo dynamics, by the way. Because if you go to, yeah, so yeah, I absolutely agree with you. Okay. Oh, you run the evolution forward and backward in time. Yeah. So because if you go to this, if you go away from the simple kinetic equations, then let's say the two-time, they don't necessarily have an entropy that only increases as a function of time. Yeah. So so you can potentially describe something. Okay, and then maybe the last thing that I want to mention that has been hardly looked at so far are hydrodynamic long-time tails, and this is especially been pointed out by Achim Roche and collaborators, and so it is actually well known from classical many particle systems that So the kinetic equation basically gives you typically exponential behavior, for example, in something like the velocity autocorrelation functions. And it's actually been known for more than 40 years that this is not correct. Yes, you get this hydrodynamic long-time tails. So the eventual approach to equilibrium is actually power law-like and not exponential. And that, and so Achim has pointed this out very much. So in a way, what is kind of missing out here would be something what one could call global equilibration. So the buildup of fluctuation patterns. And this typically happens on, this happens with power laws, so much slower. And it is not described by a kinetic equation or a quantum Boltzmann equation. Yeah? So this is something basically, I mean, where this molecular chaos assumption is not valid anymore. And this is well known from classical systems. And so they have very nice, let me just show you, they have very nice numerics. A paper by them, I only have the archive number right now, which is hardcore bosons in a specific limit where they can simulate large systems for long times. And here they look at basically, so this is just the energy of dispersion relation is essentially the energy of particle I, and this is the energy of particle I+1, and they look at the correlation function of this. And in the Boltzmann equation, this would be completely uncorrelated, by the way, so that there should be no correlation. And what you actually find here is a beautiful power law behavior. Yeah? So this is one of these hydrodynamic long-time tails. And here they look at the, this is the expectation value. Well, I would need to look this up again. So, but this is one of the examples for this hydrodynamic long-time tails. And if you have physical observables that couple to this, so in this case, for example, they couple to the local energy density, then your physical observables will also show this hydrodynamic long-time tails. So the global equilibration is actually not going to be exponential, but power law-like. So that's kind of what's missing in this picture over there and has hardly been investigated so far, apart from this one or maybe one or two other papers. No, this is. I think this was probably a 2- or 3-dimensional study, the first study on this. Yeah. Classical system, yeah. This is now a 1-dimensional system. This is a 1-dimensional system. Yeah, exactly. But it's basically a bosonic Hubbard model with very large U. So you can basically think of it as, you can basically deal with it in a classical simulation because you have just few excitations. And they basically, you can just describe their scattering processes classically. So you cannot describe their creation classically, but once you have created them, you can describe the scattering processes classically. And that's why they can go to pretty large systems. These power laws depend on the conservation laws. For example, if you have additionally momentum conservation, it changes the power law. Exactly. Yeah. Yes. As far as I remember, yes. Yeah. I know they have a discussion about this. I think so. Yeah. So again, I just want to point this out. This hydrodynamic long-time tails is, I think, something that has not been discussed a lot so far, and we would generically expect to find that. Of course, it's going to be very hard to find that in small numerical simulations, but we would expect it to be generically there, and that would extend this picture over there of how we would expect thermalization to take place, basically on a global level. Yeah, so this term global equilibration actually would come from a situation where you look at a system that is not spatially homogeneous. Yeah, so where you have basically where your kinetic equation dynamics would give you locally some, some temperature, but you could still have different temperatures in different regions or different energy densities in different regions. And now you have energy diffusion, which is basically a hydrodynamic equation, and that's why it takes much longer. Yeah. Here one is dealing with a system which is spatially homogeneous. So what global equilibration actually means is that you have a certain fluctuation pattern in your energy density at one point and at the other point. Yeah, so you have a characteristic fluctuation pattern of the energy fluctuations at different points in your system, and that takes a longer time to build up because again, energy is globally conserved. It's a conserved quantity. So, No. This is a global quench. They are doing a global quench. Yeah, and they're really looking at here at the correlation function. Basically, as a correlation function, you measure the energy of this particle and this particle. Yeah, not for all. Not for all. Yeah, not for all. Yeah, not for all. Yeah, exactly. You somehow need to couple to the slow modes. Yeah, but you would always expect them to be there. I mean, in a closed system. Okay, the moment you make this an open system, energy is no longer conserved, and things will be exponential. I actually think it's a bit different from that because from what I know in classical systems, what you introduce is you introduce a noise term on the right-hand side. So I would expect something similar is necessary for the quantum version. So I was recently at a workshop in Bad Honnef, and there was a poster by someone in Achim Roche's group, where they are trying to do precisely this, basically introducing a noise term on the right-hand side of the Kalanov-Bain equation, basically, and seeing if this works. Yeah. But I think that hasn't, at least I think that hasn't been done so far. Kind of the question is kind of what's the minimal thing you need to do in order to capture this for a quantum system.